Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants. And today we'll be discussing percent composition. So our first question asks, calculate the percent composition of each species of H2SO4, sulfuric acid. The first thing we want to do is to calculate the molar mass of each species, and then from there calculate the molecular mass. Well, we can determine the molar mass simply by looking at the periodic table of elements. So we find that for hydrogen, it's 1.008 grams per mole. Sulfur is 32.07 grams per mole. And oxygen is 16.00 grams per mole. So that's hydrogen, sulfur, and oxygen. From there, we can determine the molecular mass of sulfuric acid. So our mass is equal to 2 times the mass of hydrogen plus the mass of sulfur plus 4 times the mass of oxygen, the molar mass of oxygen. And once you've done the arithmetic, you'll find that the molar mass of the molecule of H2SO4 is 98.09 grams per mole. Well, when we're discussing percent composition, we're only going to worry about the grams. So we're going to just assume that we're dealing with 1 mole. So let's get rid of that mole, and we're going to find that our actual value will be 98.09 grams. Then it's just a simple matter of calculating the percent of each species, the percent composition, and recognizing that these percent compositions, once calculated, should add up to 100%. Fairly simple. So let's start with hydrogen. Percent hydrogen should equal 2 times, because there's 2 hydrogens in sulfuric acid, 2 times 1.008 grams all over the mass of the molecule itself, which is 98.09 grams. Then you multiply that value by 100% to get our percentage, which when you do so, you'll find it to be 2.055%, which is roughly 2.06%. And you'll see why I rounded it to 2.06 here in a minute. Percent sulfur is equal to 1 times the mass of sulfur, so 32.07 grams, over 98.09 grams, which is equal to 0.3269 times 100% will equal 32.69%. And finally, the mass of oxygen as a percentage. Is 4 times the mass of oxygen. And we use 4 because there are 4 oxygens in the chemical formula. 4 times the mass of oxygen times the mass of sulfuric acid times 100%, which gives us 65.25%. If you were to add up the 2.06 and add that to 32.69 and then add that to 65.25, you would find that the value ends up being 100. Therefore, we have done this correctly. The next problem asks us to calculate the mass in kilograms of iron in 7.31 times 10 to the third kilograms of iron 2 oxide. So, looking at this, first thing we need to do is to calculate the molecular mass. Well, the mass of iron, Fe, is equal to 55.85. So 55.85. Again, we're just going to worry about grams for now because we'll be relating that to a percentage here in a moment. And we're only considering that we're dealing with 1 mole when we're dealing with percentages. And the molar mass of oxygen is 16, as we demonstrated in our previous problem. So 16.00 grams. So our molar mass for the molecule, or let's just say our mass for the molecule, is 2 iron, so 2 times 55.85 grams plus 3 oxygens, which is 16.00 grams. And that gives us 159.7 grams. So that's our molecular mass for iron oxide. And looking at this, we do have the proper number of significant figures, which is 4. Now we need to find the percent of iron. We don't have to worry about oxygen. It's not asking about oxygen. It's only asking about iron. So let's just find the percent iron. So percent iron is 2 times, because there are 2 irons, the mass of iron, which is 55.85 grams, over the mass of the molecule, which is 159.7 grams, which would equal some low amount, which is 0.6994. Now, I didn't put this in percent. I'm simply looking for the decimal equivalent because we're then going to relate it back to find the number of actual kilograms of iron. So then all we have to do is a dimensional analysis to find the mass of iron, recalling that this up at the top is our mass in kilograms of iron oxide. So we are looking simply for the mass of iron. So the mass of iron is going to be our percent of iron given in decimal form of 0.6994 times the given mass, which would be 7.31 times 10 to the third kilograms. Which, when you do your arithmetic, comes out to be 5.11 times 10 to the third kilograms. That's it. That's all there is to it, to getting the mass of a species inside of a molecule given the mass of the molecule itself.